So we've already talked about the stiffness displacement method for solving indeterminate axial problems. We're going to throw another kind of wrench into the mix, and we're going to add temperature effects as well too. So the problem that we have here, we don't have any externally applied loads. It wouldn't be a problem if we do. But in this case, all that we have is this assembly. It's fixed between points A and B. And even though there's no externally applied loads, we do have a change in temperature. We go from positive 12 degrees centigrade to positive 18 degrees centigrade. And there's a lot going on in terms of the materials and the geometry here. We go from steel to brass to copper. We have different lengths. We have different cross-sectional areas, and we have different materials, obviously. And so A, E, and L, the three different properties that can change the stiffness of a member, all of those vary between the different parts of the assembly here. So unlike some problems where we've said, well, all the members have the same length, so that doesn't affect stiffness relatively, in this case, all the possible ways that we can vary stiffness are varied. But it's just a little bit more algebra. It doesn't really change the way that we go about the problem. We're also given the property here. This will also make a difference as well too in terms of how much each of these sections want to expand or contract. It's the coefficient of thermal expansion alpha. We have different values for each of those as well too. So all that this problem is asking us for is what the support reactions are going to be at A and at B. And we'll see that both A and B are going to have the same support reactions just based off of statics. And again, once we have that, it'll become a determinate problem, and we could figure out what the stress is at any point. We could tell what the deflection is of any of these members. Again, the deflection of the change in length. At this point, because we have temperature involved, the displacement is going to be a superposition of force-based effects, or NL over AE, plus the temperature displacement, which would be alpha delta TL. And we can also look at the transverse displacement as well too, which we'll talk about. So we're going to solve this problem two different ways. One way is going to be using the stiffness displacement method. The other way is going to be using the force flexibility method. Either way we'll get to the same exact result. So let's jump into the solution. And because we're using the stiffness displacement method, we have a very formulaic way that we solve it. Step number one is going to be that we look at equilibrium. Step number two is when we look at displacement, compatibility. So here in terms of equilibrium, we're trying to figure out the relationship between all of these internal normal forces for these three different sections. So the way that we would figure out an internal normal force would be to make a section cut through any of these sections. Okay, well, we're going to find out. Let's just say that I want to make a section cut here between in the steel member and a section cut in the copper at the same time. There's no problem with making more than one section cut at a time. It's always going to be in equilibrium. You just might get yourself in trouble getting more unknowns than you can solve for, but here it won't be a problem. So let's make a section cut through the steel and a section cut through the copper at the same time. We'll keep the portion of this assembly between those section cuts and see what happens with that free body diagram. So we'll end up with some portion of the steel member. We'll get the entire portion of the brass in the middle, and then we'll get some portion of the copper up into the section cut. So here's my section cut through the copper. Here's my section cut through the steel. And so I can show what my internal normal force going through the steel would be. Let's call it N sub S for the internal normal force in the steel. Again, I've drawn it in the assumed positive direction going away from the section cut. My internal normal force in my copper, it's the same sign convention. I'm going to draw it pointed away from the section cut. Okay? I have no other externally applied forces. And so what I'm going to have here, if I run equilibrium, I'll show my coordinate system. And if I sum the forces in the x direction equal to 0, I'm going to get that just summing everything up, minus NS, minus the normal force in the steel, plus the normal force in the concrete is equal to 0. I was trying to skip a step, but I wanted to be as verbose as possible. So I simplify this and I get the internal normal force in the steel is equal to the normal force in the concrete. And that should make intuitive sense by now, because over the entire length of this assembly, between the supports, we have no external forces applied. We will have a reaction at A, we'll have a reaction at B, but between those there's no intervening axial forces. So it makes sense that the normal force can't change from just inside of A to just inside of B. So the normal force in the steel and the copper is going to be the same. If I were to cut this free body diagram short, where I go instead of through the copper but through the brass, and I have my internal normal force in the brass shown right there, I would also find out that all of these are equal. The normal force in the steel is equal to the normal force in the copper is equal to the normal force in the brass. So we don't get a lot out of our equilibrium equation for this, other than we know that the internal normal force between all of these is the same. So it's still indeterminate. This step still tells us that it's indeterminate because we know some relationship between these, but we don't know what the actual magnitude is of each of these normal forces. And again, if we had externally applied loads, that would show up in this equilibrium step. Okay? So this is really our equation number 1. Most of our work is going to get done in the compatibility step, which is next. But this is really all that we can glean from the equilibrium step for this problem. All right, so step number 2, like I said, is where most of the heavy lifting gets done. Step number 2 for the stiffness displacement method is compatibility. And again, compatibility is telling us something about the relative displacement of each of these members. And so what we want to do is we're going to show the original system. We have steel, we have brass, we have copper, and we need to figure out some way to write an equation that captures how the change in length of each of these members is going to be relative to each other. And with this assembly, it's a little bit trickier. Often we've dealt with just 2 independent sections, but there's nothing from keeping us getting a good equation for this based off this diagram. So we know that between points A and B, we can't have any change in length. So whatever this overall length is, which I'm going to represent as L naught, we know that L naught is going to be the same, the original length is going to be the same as the final length. So the final length is going to have to be through the same, between point A and point B. It can't move, that's our final length. So we know that the original length, L naught, is equal to the final length. Okay, and both the original length and the final length is going to be the sum of the length of the steel plus the length of the brass plus the length of the copper. Both those will be equal to those. One is going to be the undeformed lengths, the other is going to be the deformed lengths. Again, the steel, the brass, and the copper, they can change relative to each other as long as when they all add up, they're the same original length in their final condition. So the steel could get an inch longer as long as the copper and the brass combined together get an inch shorter. That's what we're trying to say here. So another way to put that is that the original length is equal to the final length. We can simply rewrite the final length as equal to the original length plus the change in length. Okay? We can break down this delta even more. We can say that we're going to keep the left-hand side, the original length, is equal to the original length, but instead of delta, I'm going to break this up and I'm going to say that delta is going to be the superposition of two different changes in length. So one change in length is going to be due to the thermal effects. All right, we have a change in temperature, so we'll get some alpha delta T, some change in length due to the change in temperature. But the change in length is also going to be due to the forces that get induced in this system. So I'll have some change in length here due to the change in temperature. So I have the change in length due to delta T plus the change in length due to the internal forces, which I'll just say is capital N for the internal normal forces. And we can already see with this equation that L naught cancels out. I can just subtract L naught from each side. And so I can rewrite this and I can say that the change in length due to the change in temperature plus the change in length due to the normal force is equal to 0. All right, so now we're getting somewhere because we know how to represent both of these changes in length in terms of normal forces and other properties that are given over here. So the change in length due to the change in temperature, that's simply equal to the summation for all of these three different parts, the steel, the brass, and the concrete, of alpha times the change in temperature times the original length. Right, we already have all of these numbers. Delta T is going to be the same for each of them. Delta T is simply T2 minus T1, or in this case it will be positive 6 degrees centigrade. We already have the alpha for each as well too. That's a material property. Alphas are listed out here for steel, brass, and copper. And the original length, that's for each segment, we have that as well in our table. 0.3 meters, 0.2 meters, 0.1 meter. So this entire term right here, we can calculate that and we'll actually get a distance in meters or millimeters for that. All right, so that's the first term. We can also write out what the second term is going to be, and we can say that that's equal to the summation of NL over AE for each of those parts. This is all going to be equal to 0. So again, L's we already talked about that. We could even cancel all those out if we want to. Actually, we can't really do that. We have the cross-sectional areas that we don't even have to calculate it for this problem. It's already given to us. 200 millimeters square, 450, and 515. And the modulus of elasticity for each of these members, that's given to us as well too. So the only unknown that we have in this equation anymore is the internal normal force in each of those three members. So I guess technically at this point we have three different unknowns. We have the normal force in the steel, the normal force in the concrete, and, the copper, and the normal force in the brass. But we already know from up here that all of these are equal to each other. So I can just basically say that all of these are equal to one single unknown variable, capital N. So I just have one unknown. I've taken three unknowns, which would be the summation of these three different terms, and I've said that they're all equal to each other. Okay, so one equation, I've got it down to one unknown by applying this equation up here. So technically this is equation number 2, but it's really where all of our work is being done. And now all that I need to do to solve for the internal normal force is simply put in all of our values here. So if I was going to do, let's just do the alpha delta T part in green. So I'll go steel, brass, copper. So the alpha for the steel, 12 times 10 to the negative 6 over degrees Celsius. So 12 times 10 to the negative 6 over degrees Celsius times the delta T. It's going to be the same for all of these, which is positive 6 degrees Celsius, times the length of the steel, which is 0.3 meters. All right, that's going to be plus the same term for the brass. So it's 21 times 10 to the negative 6 over degrees Celsius times positive 6 degrees Celsius, that's the change, times the length of the brass, which was 0.2 meters, plus the last term for calculating the change in length due to the change in temperature is going to be for the copper. alpha is 17 times 10 to the negative 6 over degrees Celsius times the change in temperature, which is 6 degrees Celsius, times the length of the copper, which is 0.1 meter. Okay? All three terms right here just represent the change in length due to the change in temperature. And then I'm going to add together with that the three terms corresponding to the change in length due to the force-based effects. So all those will have the same unknown normal force because it's a constant normal force from A to B. And so I'll do these in blue, and we will get, for the steel, the internal normal force is unknown. The length is 0.3 meters. The area is given to us here as 200 millimeters squared. So that's going to be 200 millimeters squared times 10 to the negative 6 to get that into meters squared. So our conversion factor is simply 10 to the negative 6th. And the modulus of elasticity of steel is 200 times 10 to the 9th pascals. All right, so that's term number one. That's for the steel. And then we're going to do the second term, which is going to be for the brass. All right, we still have the same unknown normal force N. The length of the brass is 0.2 meters. The area of the brass is 450 millimeters squared. We have to multiply that by 10 to the negative 6 to get it into meters squared. So 450 times 10 to the negative 6, that's going to get us into meters squared. And then we just multiply by the modulus of elasticity of the brass. That's given to us as 100 gigapascals. I'm sorry, 100 times 10 to the 9th to get everything in the same units. And then our last term is going to be for the copper. We have the same internal normal force because it's constant the entire length of the column, times the length of the copper, which is 0.1 meter, divided by the area. We have 515 square millimeters. We'll multiply that by 10 to the negative 6 to get it into square meters. Oops, 515 times 10 to the negative 6 to get it into meters squared, and then times the modulus of elasticity of the copper, which is 120, times 10 to the 9th pascals. Okay, and this is all equal to 0. So again, everything in green, these three terms on the left, that's the change in length due to temperature. These three terms at the bottom, those are the change in length due to the force-based effects. We only have one unknown, the internal normal force. And so, let me free up a little bit of space. I get that the internal normal force for all three members is equal to negative 4.2 kilonewtons. So that passes the only reasonableness check that we can do, simply that's telling us that the steel, the brass, and the copper are all in compression. And if we're heating up this assembly, it's going to push up against the supports A and B. So the fact that this is a negative value is reasonable. That passes kind of the smell test. And so then our reaction at A and our reaction at B, R sub A, R sub B, in the direction that I've shown them right there, is simply going to be equal to the magnitude of the internal normal force. So those will be 4.2 kilonewtons. Those are going to be the reactions. I want to talk a little bit more, so that's the final answer in terms of what was required for this problem, but I want to talk a little bit more about how we would calculate the changes in length for each of these elements. So when we start looking at problems like this, indeterminate problems where we have temperature involved, it's really important to keep track of the changes in length or diameter and the strains for temperature and force-based effects completely separately. So let's just have a break line here. And so let's say that we wanted to figure out the change in length of the steel. Again, we know the overall change in length of the steel, the brass, and the copper combined has to be 0, but that's not to say that the steel itself couldn't get longer or shorter, and that would be made up by the brass and the copper. So anytime that we're trying to calculate the change in length of any element in the longitudinal direction, so the change in length in the longitudinal direction, it's always going to be a superposition of the force-based effects and the temperature-based effects. So I'll always have some force-based effect, and I'll keep the subscript longitudinal because we're going to talk about transverse in a second, plus the change in length due to the temperature-based effects also in the longitudinal direction. So let's assume that we have a constant normal force, a constant cross-sectional area, so we can simplify this down to just that ratio. We don't have to use the general integral form. And let's just say that if it works out that way, this is just going to be NL over AE. And we've already talked about the change in length due to the change in temperature in the longitudinal direction. That's simply alpha times delta T times L. Okay, so I could plug in the internal normal force that we just calculated for the steel. I could plug in all the material properties and the geometric properties, and I could calculate what the change in length of any of the steel, the brass, or the copper members would be. And again, each of those individually probably isn't 0, but when we add them all up together, they're going to be 0. That's the longitudinal direction. Again, the change in length in the longitudinal direction. That's relatively straightforward. But again, a lot of times people, even though they've gone through the work and they realize that we have a change in temperature and an induced internal normal force, they'll often only look at one of these terms. But remember, even if you don't have a temperature on your problem, you might even want to just write this out, this general longitudinal deflection equation, having both these terms and then just checking off and just saying, okay, well, we don't have any change in temperature, so I'm just going to make that term 0. But again, this is the more straightforward of the two different deflections or displacements because we can also have a transverse change in length as well too. So in that case, we're talking about how would, say, the radius or the diameter of any of these elements change. If we're looking at the transverse change in dimension. So it starts out the same way. It's always going to be a superposition of the force-based effects and the change in temperature effects. So we'll say that delta trans is going to be equal to the change in transverse dimension due to the normal force or force-based effects plus the change in that transverse direction due to the change in temperature. Okay, but it's not so straightforward in the sense that we don't have NL over AE for the transverse direction. This is purely a longitudinal effect. And then over here, alpha delta TL is just a pure longitudinal effect as well too. And so the way that we analyze this, let's look at the force-based effects first. We know that if we have a longitudinal member here, and let's say that we calculate the strain in the longitudinal direction, we can then calculate the strain in the transverse direction as long as both of these are just based off the force-based effects. And the way that we relate the transverse strain to the longitudinal strain is with Poisson's ratio. And again, the important caveat here is that Poisson's ratio only applies to strains that are force-based, not the temperature-based strains. So Poisson's ratio is equal to minus the lateral or transverse strain divided by the longitudinal strain. But again, I'm going to put a subscript here that both of these are only due to the force-based effects, or the normal force. So when we calculate the longitudinal strain, we only want to calculate the longitudinal strain due to the internal normal force. And so often the way that we rearrange this equation is to solve for the transverse strain. So the transverse strain due to the force-based effects is equal to minus Poisson's ratio times the longitudinal strain, but only the longitudinal strain, or the portion of the longitudinal strain due to the force-based effects. And if we have a problem where the internal normal force and the cross-sectional area is constant, in other words, if NL over AE applies, then to calculate the longitudinal strain due to the force-based effects is really easy. We say that longitudinal strain is equal to the change in length divided by the original length. If my change in length is NL over AE, that's the numerator up here. So that's NL over AE divided by L. All that I'm doing here is I'm just canceling out the L's. And I can say that the longitudinal strain is equal to N over AE. And you can work out the units for that. You'll see that it's going to be in units of distance per distance, or strain. So I can simply take that N over AE and plug it in down here. And I get minus Poisson's ratio times N over AE. And again, if I want to get to my actual displacement due to normal forces in the transverse direction, that's simply going to be equal to whatever my transverse strain is due to the normal forces times my original width, or D naught. We've already calculated what this term is, so I get minus Poisson's ratio times N divided by AE times D naught. All right, so this entire term right here will tell us the change in the transverse dimension only due to the force-based effects. All right, there's a lot that goes into that, but the most important key is that Poisson's ratio only relates to the force-based strains. All right, that's the harder of the two to calculate. The change in the transverse direction due to the temperature change is really straightforward. Again, if you remember our longitudinal change in length, actually I have it right here, our longitudinal change in length due to a change in temperature is simply alpha delta TL. And so if I wanted to calculate what my strain is due to a change in temperature, it's simply equal to the change in length over the original length. My change in length is alpha delta TL. So that's divided by L, and the L's cancel out. So I get that my strain due to the change in temperature is simply equal to alpha times delta T. And so for temperature-based strains, it's the same in the longitudinal and the transverse direction. It's the same sign, it's the same magnitude. Unlike force-based strains, where the transverse direction is an opposite sign and it's a different magnitude, for temperature-based strains, it's always alpha delta T, regardless of which direction it's going. So then all that I pull this in, but I'm going to multiply it by the original transverse dimension. So this simply becomes alpha delta T times D naught. And we bring over here minus Poisson's ratio times N over AE times D naught. And so just to write that all out in one place, the change in the transverse direction is equal to minus Poisson's ratio times n over AE times the original transverse dimension plus alpha times delta t times d naught. Okay? So this, the caveat on this is that for this term to apply, NL over AE has to apply. In other words, it has to have a constant normal force the entire distance of whatever member you're looking at, and it has to have a constant cross-sectional area across the entire length of the member that you're looking at. And then this will apply. And we're keeping completely separate the force-based effects from the temperature-based effects. So the bookkeeping is the most important thing here, but other than that, it's just some simple algebra to calculate the transverse change in direction.